I'm going to talk about the flow that's generated by an oblique impact of granular material on an inclined plane. This is some work I've been doing during my PhD at the University of Manchester with Nico Gray. So the situation is as follows. I have a funnel containing sieved sand of diameter less than 0.6 millimeters, held at a distance above an inclined plane, and the material flows from the funnel, impacts the plane at a point, and then forms a flow which goes down the inclined plane. The plane is it's untreated hardboard, so it is rough, perhaps on a scale of 0.2 millimeters. So it's not a very frictional surface, but neither is it perfectly smooth. And just to give you some idea of the scale of the experiment, the diameter of the funnel is 15 millimeters. The height here is about 250 millimeters, and the angles that we're looking at are around 25 degrees. And I'll show here a video of what the flow looks like. The granular material impinges in this region and flows down the inclined plane.
Is that in the middle a full granular vacuum?
Sorry?
Is deep region in the middle a full granular vacuum?
It's not a full granular vacuum. There is something flowing. So we have the flow is time independent. It reaches a steady state, as we saw in the video, and we have a closed hydraulic shock here. And in the interior, there's a region of thin, fast-moving radial flow. So this is the region in which there is the material impacts here at a high velocity and forms a very thin sheet of fast-moving flow in this region, before moving through the hydraulic jump into a region of slower flow, which then moves down slope and forms a steady flow down slope in the same way that we saw in Daisuke's talk earlier. Now, the flow in the slower moving region, though it is slow moving, is still supercritical on both sides of the shock. So the flow here is very fast, the flow here is slower, but is still supercritical. And we can see that evidence of that here, that the two shocks here collide at an angle, a sharp angle. So there's no information from the shock collision point here is propagated upstream. So on the basis that the flow in the majority of the inclined plane is thin, we use thin air modeling based on the Savage-Hutter theory. So we have equations of mass conservation and momentum conservation. So we depth average, we're working in depth average velocities and flow depth. Now, what we're doing here is removing almost all of the rheology. You can see here we're not using an earth pressure coefficient, but we just want to see how much we can get just from a pure sort of shallow water type model. One important property of this is the friction coefficient, and we're using the friction coefficient of the Pouloucan theory, so that's dependent on UNH. So these are hyperbolic nonlinear system conservation laws, and we solve them using a simple finite volume method. So just to give a bit more detail about the friction law, in the experiments we see that thin regions become stationary, so we have a definite H stop. And we also see that there's a steady uniform flow over a range of slope angles. So despite the fact that our plane is not totally rough, we still think it's justified to use, there's evidence that the Coulomb law is not the correct model here. So with these equations, we can simulate them numerically using the methods I mentioned now. there's one region where the flow is not shallow, and that's the region of impingement, which is here in the numerics. Now, as we heard in the previous talk, the shallow water equations don't model the column collapse problem well at all, and they won't model the problem of a very tall column collapse, which is essentially what we have here, the continuous flow from a funnel hitting the plane. So instead, we use an analytic result from inviscid flow. A simple Bernoulli's law and momentum conservation can give a distribution of height and momentum radially around this point. So then we apply those boundary conditions in the numerics in a small circle around the inflow point, and then simulate the shallow water equations elsewhere. And we see something not dissimilar to experiments where this region forms a very fast radial flow, a hydraulic shock, and a region of slower downslope flow. Now, we currently don't have the ability to experimentally determine the friction law parameters, so the values of mu and their dependence on height and velocity. But so these results are at the moment qualitative, but we can see that there is there is at least qualitative agreement with the shapes that we see in experiments. So experimentally now, we'd like to determine some scalings perhaps on the size of this region. So we can take possibly the width of it and the length of it, and we'd like to know how these scale with d, the funnel width, and also on h and theta, the height of the funnel above the plane and the angle of the plane. Now, here I make a correction to the height because the material moves out of the funnel at a finite speed, and perhaps a more relevant quantity for scaling is the sort of virtual origin, which would be the point at which the material is released at a velocity of 0 and then falls ballistically. So we can define a small correction to the height, called h virtual, which is just the height from the bottom of the funnel to the plane, plus a small correction which extrapolates up to the point at which the material would be stationary. And what we see, this is the virtual funnel height and then the width and length of the shock region. We see some very linear scalings, though here there's definitely a constant offset, which we're not quite sure the origin of. We think it might be, it's somewhere close to the diameter of the funnel, but that needs further experimentation. Now the dependence on theta is slightly more complicated. So if we collapse these down onto a single curve, we don't see, there's no obvious scaling for the length of the length or the width of the shock region on theta. But there's obviously more than one mechanism at work, because for relatively flat, relatively shallow angles and for high heights that the material is dropped from, we see a different pattern altogether, which is these blunted shocks. So this is a view of the inflow region, but instead of forming a shock, instead of the shocks meeting at an angle, they instead form this rounded, blunted shock with some complicated behavior going on here. And here's that from another angle where you can see how the shocks, these shocks, which we see here, then sort of curve round and collide in a complicated region and to form the slower flow downstream. Now, one thing which we see in these is a persistent ridges which are seem to be generated by this region of flow here, and which persist all the way down to the bottom of the slope, a bit like the a few days ago we saw some videos of snow avalanches, in which there were persistent features on the top of the avalanche because there was no shear at the surface. And that seems to be what we're seeing here, in that the material on the far side of the shock in this region seems to be shearing mainly at the base, and so the top layer of it is just moving in a solid block and is able to sustain these dents. But while we can reproduce with the numerics in the correct parameter regimes the blunting of the shock, here we get a third shock coming in. Obviously, because we've thrown away much of the rheology, we don't get the persistent dents. Now, we have a theory as to why the distinction between the two regimes, and that is, I mentioned earlier, both in this region and this region, we have Froude numbers of greater than 1. However, the Froude number in this region is less than 1. So we have a strong shock which propagates up here, and this strong shock only exists only overlaps the region, this teardrop-shaped region, for sufficiently low angle. So experimentally, we've performed some parameter studies on H and on theta, and we see a fairly well-defined phase diagram of regimes for sufficiently low angle and also sufficiently low height. We don't actually see any shocks. The material just spreads out onto the plane with no rapidly moving region and no shocks. But if we get to high enough heights, then we see either the teardrop-shaped or the blunted shocks in fairly well-defined parameter spaces. So the two videos I've shown existed about here for the teardrop shocks and about here for the blunted shocks. Now you'll see down here that below a critical angle we see only unsteady flow. All these flows above here are steady. Here there's unsteady flow, and that's really there's some quite complicated behavior in this regime which we don't fully understand. So I'll just leave this video playing. This is with a smaller funnel diameter, and you can see here that this material is actually stationary. So this is at below a height less than H stop. So it goes directly from the very rapidly moving region to stationary material. Now as the shock propagates in, we get some unsteady avalanching behavior. And if we, I should have speeded this up, if we leave this avalanche behavior, eventually this will change again into the original flow, but this time we've got significant levees on either side, and these direct the flow quite strongly. So that oscillation continues for about 8 or 10 times until there's enough stationary material on the slope that a channel is formed which actually directs the flow in what seems to be a steady path down the slope. Now we can't model this with just the shallow rheology, but there's obviously some interesting behavior in there to be looked at. Thank you.
Let it play during the question.
Sorry?
Video play during the questions. I want to see it show up, go 10 times.
Don't know how far this one goes, but
So some questions in the video?
Oh, that was as far as it went? Okay.
it will go further, but I'm not sure if it gets to steady state.
Well, you see it right here. Below the tip of the teardrop, there seems to be, a crest.
Yes.
Is that the merger of the two shock fronts that come from left and right?
Yes.
And form the new shock, which is the symmetry line?
We don't think there's a shock on the symmetry line. When in the shallow water case, there's been a paper by John Ockenden and co-workers about what they call, I think, hypercritical flows, where if two shocks collide in that sense, the material is directed vertically upwards, and you get a sort of the material, some material jumps out of the flow, and that's what you're seeing to a certain extent there. So it's the sort of the increase in pressure as the material flows in, then causes a sort of bump.
Is there no discontinuity?
There doesn't appear to be discontinuity.
Why do you call it intermittent flow? It seems to be pretty, well, there are several regimes of flows, but they seem to be occurring pretty regularly. The time interval between one type of flow and the other one.
In this regime, I just use intermittent to mean unsteady, I guess.
Okay, good. That's what
Yeah.
what I meant. But it is really pretty regular.
Yes. I mean, we don't. I mean, in Daska's paper presentation earlier about the flow down the experiments in Cambridge, he saw very regular avalanches. Now that's not what we see here. The period is different. Varies, and of course we don't have anything like the same sort of time. We don't see hundreds or thousands of oscillations to measure that. So.
Why hardboard and not sandpaper?
It's primarily a problem of how to stop the material from bouncing when it hits the plane. The reason we're using sand rather than glass beads is because the coefficient of restitution is sufficiently low that the material does spread out over the plane. Most materials in our lab, if we try them, it falls down, hits the plane, and just bounces off and goes everywhere. And so, if we use a very rough material, everything is much more frictional, so all our phenomena are much smaller. So we have to use higher heights of the funnel, and then that causes more material to spray out rather than remaining in a thin air flow. So it's sort of a practical issue, but it'll be interesting to see what the effect of friction is on this.
Okay, I think we have to